Today we're going to look at the Millikan Oil Drop Experiment. That's the experiment that determined that the elementary charge is that number 1.6 times 10 to the minus 19 coulombs. The basic idea in the Millikan Oil Drop Experiment is we want to get a bunch of small objects that have very small charges on them. And when I say small charges, I mean 2 extra electrons or 4 extra protons or 7 extra electrons. Small numbers of that elementary charge so that we can kind of work backwards and figure out what the elementary charge is. So the way that we get small objects with small charges on them is to use an atomizer, one of those things we use to disperse perfume. And we put some oil into the atomizer, we squeeze the bulb, and we get out some spherical oil drops. And of course, each one of those oil drops is going to be a little different from the others. Each will have its own mass, and each will have its own charge. And the way it gets the charge is because there's some friction along the way. And that friction tends to rip electrons off, either from the oil drops or from the atomizer itself. So each one of the drops has its own mass and its own charge. If we now suppose that we take our atomizer, we squeeze the bulb, and we push some oil drops out between some parallel plates, and we'll have a variable voltage attached to the parallel plates, which means we're going to be able to adjust the voltage, adjust the electric field between the plates. The electric field would just be given by the voltage across the plates divided by that distance. And what we're going to try to do is change that electric field so that we get the drop to be suspended. So if it is suspended, we know the forces must balance, and the two forces acting on the drop would be the weight of the drop and that electric force upwards. So they're going to have to be equal and opposite. So we could say that mg must be equal to the electric force. And the electric force will be given by whatever the charge is on the drop times the electric field, which is the V over D. That will equal mg. We would now like to write the mass in terms of the radius of the drop and the density of the drop. So mass is equal to density times volume. So if we take the density of the oil drop and multiply it by the volume of the drop, 4/3 pi r cubed, times g, then that should equal q times v over d. Now we can arrange that to solve for the charge on the drop. And that's just going to equal the density of the oil times 4/3 pi r cubed times g times d, all divided by the voltage that you're putting across those plates. And what we want to notice here is that we know all these quantities, right? We know the voltage across the plates. We know the density of the oil. We know the gravitational field. We know the distance between the plates. So what we need to figure out here is what is the radius of the drop? How big is our drop? So that's our big question now. If we can find R, then we're going to be able to determine the charge on the drop. And that's what we're really after, the charge on the drop. In order to find out the radius of the drop, what we do is we just let the drop fall due to gravity. So there will be a gravitational force downwards, of course, and there will be a resistive drag force which becomes larger with speed. So this is one of these situations where it's going to reach a terminal velocity, and it'll reach that terminal velocity very quickly. So we're following our one drop, the drop that we started with. We turn off the electric field, use our microscope to watch that oil drop fall down, and it'll very quickly reach terminal speed, and we're going to measure that terminal speed. So the drag force is given by Stokes' law, so it's going to be 6 pi viscosity of air times the radius of the drop times the terminal speed that's reached. Now there is a buoyant force involved, F B for buoyant, But it turns out to be very small compared to the drag force, at least when the drop is moving at that terminal speed. So what we're going to do is eliminate that. It'll be left as an exercise for you to figure out what happens when we include the buoyant force, how the formula changes essentially. So this time we're going to be able to say that 6 pi nRV equals mg. Same trick as last time for the mass of the drop, so that'll be the density of the oil times 4/3 pi r cubed g. On this side we've got 6 pi. Viscosity of air, the radius of the drop, and that terminal velocity. So now what we can do is cancel out the pi. We can cancel out one of the r's as well. So we can solve for the square of the radius of the drop, and that's going to be equal to 6 eta v divided by the density of the oil times 4/3 g. And then we can take the square root of that, and we'll get that the radius itself will be equal to the square root of 9/2 eta v divided by the density of the oil times the acceleration due to gravity. So we can now take this expression for r and substitute it in for the r in the expression for q and work out what the charge on each drop is. Now, in most cases, what you're going to do is do that numerically. In other words, get a number for the radius and then substitute it into the second equation for the charge, rather than doing it all algebraically. So what are we expecting our results to look like if we look at lots and lots of oil drops and measure the charge on each of those oil drops? Well, it's going to be a little like if you've got nothing but $5 bills. If you've got nothing but $5 bills, then you know your total amount of money is going to be some multiple of 5. So you're going to get values like 15, 25, 95, etc. The elementary charge is 1.6 times 10 to the minus 19. So we're expecting all of the charges on the drops to be some multiple of that number. So you're going to see numbers like 1.6 times 10 to the minus 19, or 3.2 times 10 to the minus 19, or 4.8, or 6.4, or 8.0, etc. All charges are going to have to be a multiple of the elementary charge. Here's an example. Pause the video, try the question, and come back for the answer. So you want to notice that this number is really 5e, 5 times 1.6 times 10 to the minus 19. So that means that we have to have 5 elementary charges on our 2 drops. And so if you look at this combination here, 4.8, that's 3 elementary charges. 3.2, that's 2 elementary charges. 3 plus 2 adds up to 5e, and therefore our answer is D. In this question, you're going to try to find an expression for the charge on an oil drop in terms of the radius and those other variables that were parameters in the problem. And then describe under what conditions can the buoyant force be neglected. So pause the video, try the question, come back for the answer. So let's begin with our free body diagram. We're going to suspend the drop. So we're going to have an electric force pushing upwards. We're going to have this buoyant force. The buoyant force is given by the weight of the fluid displaced. So that will mean it's the density of the fluid, which is air, times G times the volume of the sphere, that 4/3 pi r cubed again. And of course, downwards, we're going to have mg. So if it's suspended, those forces must balance out. So mg must be equal to Fe plus the buoyant force. Make our usual substitutions. So the mass of the drop would be the density of oil times 4/3 thirds pi r cubed. Keep the g there. The electric force is going to be the charge times the electric field, and the electric field will be the voltage divided by the distance between the plates. And then the buoyant force is the density of the fluid, which is the air, times g times the volume of the drop, the volume of the fluid displaced. So that will also be 4/3 pi r cubed. So if we rearrange that for q, we get d over v times 4/3 pi r cubed g. We're common factoring out that term. And then you'll have the difference in the two densities, the density of oil minus the density of air. Now, the density of oil is a little lower than the density of water. And the density of water is about 800 times the size of the density of air. So typically speaking, the density of oil is about, say, 700 times as much as the density of air. So that's our condition under which we can neglect the buoyant force. As long as the density of the oil is significantly greater than the density of air. And that's going to be true for any oil that I can think of. So in summary, we kind of did two experiments. In the first one, we suspended the drop. And that meant the forces acting on it were the weight downwards, mg, and the electric force upwards. And that allowed us to solve for the charge on the drop, and it came out to be equal to the density of the oil times 4/3 pi r cubed times g times the distance between the plates all over the voltage across the plates. We then did a second experiment where we let the drop fall due to gravity. So the two forces now were mg again, but this time it would balance against the drag force, 6 pi nRV. So we're applying Stokes' law to a sphere, giving us the drag force, and the drag force gets big enough to cancel out mg, and then it goes at constant speed. And we worked out there that the radius of the drop would be equal to 9/2 viscosity of air times the terminal speed all over the density of the oil times the acceleration due to gravity. So we can work out a numerical value for the radius of the drop, substitute it in for the equation for the charge, and then we're going to work out that the charges of all the drops are multiples of the elementary charge. And that is how the Millikan Oil Drop Experiment determines the value for the elementary charge. I would greatly appreciate it if you would help to support this channel by liking videos, by making comments, by asking questions in the comments, by signing up for notifications, or by becoming a member or a Patreon. All of those would be greatly appreciated.
And that's all for today, folks. Thank you very much.